Okay guys, and we're back. So hopefully you've maybe watched the video, the previous one more time, read through the lesson again, let things sink in a bit. And now we're back trying to reinforce the concepts of electric potential and electric potential energy. So again, we've got electric potential and electric potential difference or potential difference are interchangeable. Those are those two terms. They have the variable delta big V or just plain V. So that is potential or potential difference. And the variable is the unit, apologies. The unit is the volts. And you will think of this potential or potential difference in terms of volts. Okay, we also have electric potential energy, which is given the variable EP. So your potential energy, and we're not talking gravitational potential energy, we're talking electric potential energy, which is the product of a charge's amount of charge in coulombs and the amount of potential or potential difference that it will pass through. So QV or Q delta V, same thing. On your formula sheet, you find it in the top right-hand corner of that electrostatics part or electromagnetism part, and it's shown like this. Delta V is equal to delta E over Q. And you will most often see that formula or use that formula in the form EP is equal to QV. And again, the V and delta V are the same thing. So typically we call this potential or potential difference. They are referring to the same thing, and that is the amount of voltage something has. Do that. Make sure that you write this part of the formula or this form of the formula, on your formula sheet. So it's written like this on your formula sheet, that delta V is equal to delta E over Q. And you want to write it in this form, EP is equal to QV, which you will most often see. And what that says is the amount of potential energy that a particular particle has is directly proportional to its charge and directly proportional to the amount of voltage that it will pass through, or the amount of potential difference that it will pass through on its journey. Okay, so again, some examples to reinforce that, and I'm just going to get rid of some of this stuff here. Maybe I won't yet. Okay, so I'm going to give you some potential plate or parallel plates again. And we've got a battery hooked up, whatever that is, 100-volt battery. And it's hooked up like this. So our top plate is going to be a positive plate, and our bottom plate will be negative, and we've got this electric field that exists between there. We could draw the field lines, but that's not really the intent of this lesson, so we'll leave those field lines out. And this, we'll say, is a 100-volt battery. So the amount of potential that exists the entire way across these plates is 100 volts of potential, or 100 volts of potential difference. And again, the unit is volts. The variable is potential or potential difference. Okay, so we could have two charges here. Let's say we've got an electron here. Change the color. We've got an electron sitting here, and we've got a proton sitting here. And so the question could be, compare the amount of potential and the amount of potential difference that each of these particles possess. And so this particle and this particle will experience very different types of motion when you let go of them. So if we're holding each of these here in these position with our electron tweezers, that's my term, and we let go of it, this electron's journey will look like this. Oopsie. And as it goes through from the bottom plate to the top plate, it will pass through all 100 volts of potential difference on its journey. So while it's sitting here, you would say that the amount of potential it has, which is this, is 100 volts, because that's how much potential difference it will pass through, or potential it will pass through on its journey. It has a charge of 1.6 times 10 to the negative 19 coulombs. That's the amount of potential energy it has. This guy, which is a proton, sitting at the same position, has 0 potential energy And that's because it will pass through zero potential difference or zero potential or zero voltage on its journey. And that's because when you let go of this positive particle with your electron tweezers, it's going to go nowhere. And it won't go anywhere because of the law of charges again. There's no force. There's no reason for it to move in this direction. It is being repelled by the top plate and attracted to the bottom plate. So it is sitting exactly where it wants to be. So on its journey, it will pass through 0 volts of potential or potential difference, that's here. And therefore it has 0 joules of potential energy. Yes, it still has a charge of 1.6 times 10 to the negative 19, but although the two of them are at the same position, they possess very different amounts of potential and different amounts of potential energy. So you have to look at each particle's journey. Where will it go and how much potential difference will it pass through as it moves the way it wants to go? All right, now if I erase all of this, and I'll give you a new example. Same scenario, same potential plates. So the top plate is positive, the bottom plate is negative. Oopsie. There's 100 volts of potential difference between those two plates. Now let's say that I have an electron and I'm holding it there with my tweezers, and I have a proton and I'm holding it at the same position with my tweezers. Then if we're comparing the amount of potential energy, which is this, and the amount of potential, which is this, that each particle passes through, hopefully you're thinking, well, that's the same. And it is the same. This particle, the positive particle, will move in this direction. And that's because it wants to move away from the top plate and towards the bottom plate. So this will be work done by the field when you let go of it, and it'll move downwards the way it naturally wants to go. And in doing so, it will cover half of the distance between the plates, and therefore it will cover half of the potential difference, so 50 volts. And the charge again is the charge on a proton, so 1.6 times 10 to the negative 19, and the voltage it will pass through is 50 volts. Now the electron, this one, when you let go of it, it's going to move in this direction because that's the way it naturally wants to go. It wants to move away from the bottom plate and towards the top plate. Now again, if that was exactly halfway between the plates when it started, it will pass through 50 volts of potential difference as it passes through half of the distance. And in doing so, at that position, so again, it's got a certain amount of charge, that's the charge on the electron, and a certain amount of potential difference. So the amount of potential energy it will have is the product of the charge and the amount of potential difference that it will pass through in its journey. These two are the same. They'll have the same amount of potential energy. They'll pass through the same amount of potential difference, but they're going in opposite directions. Okay, so potential difference all has to do with the amount of voltage that something will cover in the particular distance that it's traveling. So this potential again is position dependent, just like the gravitational potential was that we talked about originally. All right, I'm going to get rid of all of this and give you one new scenario. That's fun. Okay, so same parallel plates, same potential difference across the plates, or same voltage because it's the same battery. So you have your 100 volts. This is the positive terminal, making the top plate positive. This is the negative terminal, which will come down here and make the bottom plate negative. And let's say that at this position, so we've got 10 centimeters of distance across the plates, and we have 100 volts of potential between one plate and the other. And so let's say that we put something here at this position, which is 2 centimeters away from this plate. And let's say that that's an electron. Oh, that looks like 20, but it's a 2. So we've got an electron at this position, and we have a proton at the same position, which is 2 centimeters away from the top plate. Okay, and again, we're going to have to hold these two there with our electron tweezers because both of them want to move. The electron wants to move towards the top plate, the proton wants to move towards the bottom plate. So the question is, who has greater potential energy and who has greater potential or potential difference? So potential energy is EP, potential difference is that big V or delta V, and that will be measured in volts. Okay, so that again depends on where each of them are moving. The electron is moving up towards the top plate, and in doing so, it'll pass through 2 centimeters of distance, which will be equivalent to 20 volts of potential. Now why is because these two things are proportional. So 100 volts of potential is equivalent to 10 centimeters of distance. So every centimeter then would be 10 volts of potential. As this electron moves through 2 volts of potential, or 2 centimeters of distance, it will move through 20 volts of potential. And so we've got 20 volts, and the charge again is the charge on the electron. That's the same as it always is. Our proton is doing this. It's moving in this direction. And in doing so, it'll pass through 8 centimeters of distance, which is 80 volts of potential. So we can say for this particular scenario, the proton has 80 volts of potential, and the product of 80 volts times your elementary charge will give you your potential energy, electric potential energy. So your proton has more potential energy because it has more potential. The charge is the same. All right, I'm going to stop this again, give you a chance to marinate, read back over or listen to it again if you need to, and then we'll do one more video.